Before we begin, let me make something clear. Despite many viral headlines claiming that NASA is panicking or that the James Webb Space Telescope has destroyed the Big Bang, neither statement is accurate. What is true is arguably more interesting. The James Webb Space Telescope has discovered several populations of galaxies in the early universe that are significantly more massive, more evolved, and in some cases more chemically mature than many cosmologists expected. These observations are forcing scientists to re examine some assumptions about how rapidly galaxies formed after the Big Bang. That does not mean the Big Bang is wrong. It means our understanding of the earliest stages of cosmic evolution may be incomplete, and that is where this story begins. For decades, astronomers have been building a remarkably successful model of the universe known as Lambda-CDM. Lambda represents dark energy. CDM stands for cold, dark matter. Together, they form the backbone of modern cosmology. This model explains the expansion of the universe, the cosmic microwave background, the large scale distribution of galaxies, and many other observations with extraordinary precision. In fact, it has been one of the most successful scientific frameworks ever developed. When NASA, ESA, and CSA launched the James Webb Space Telescope, astronomers expected it to provide the most detailed look ever at the universe's infancy. Webb was specifically designed to observe infrared light from the earliest galaxies. Because light takes time to travel, looking farther into space means looking farther back in time. Some of the galaxies Webb observes emitted their light more than 13 billion years ago. In other words, Webb is functioning as a time machine. It allows us to observe the universe only a few hundred million years after the Big Bang. The expectation was straightforward. Astronomers believed the earliest universe would contain small protogalaxies, tiny collections of stars and gas, messy, chaotic, still assembling. The prevailing theory predicted that galaxies would gradually grow through mergers and continued star formation. Small structures would form first, larger structures would emerge later. This process is known as hierarchical structure formation. Then Webb started sending back data, and almost immediately, astronomers noticed something unexpected. Instead of seeing only small primitive galaxies, Webb identified several candidate galaxies that appeared surprisingly massive. Some appeared to contain stellar masses comparable to large modern galaxies, despite existing only 500 to 700 million years after the Big Bang. In February 2023, a landmark study led by Ivo Labbé reported 6 candidate massive galaxies observed within the first 700 million years of cosmic history. Some estimates suggested stellar masses exceeding 10 billion solar masses. One candidate potentially approached 100 billion solar masses. To understand why astronomers reacted so strongly, imagine visiting a city where construction supposedly began 6 months ago and discovering fully completed skyscrapers. The issue is not merely that the buildings exist, the issue is the timeline. According to many galaxy formation models, there simply should not have been enough time to assemble structures of that size. The media quickly labeled these objects impossible galaxies. Scientists themselves used more cautious language, terms like too massive, unexpectedly mature, challenging existing models, tension with structure formation theory. These were the phrases appearing in scientific discussions. Now, an important clarification. The first Webb observations relied heavily on photometric measurements. Photometry estimates distances and masses using brightness across different wavelengths. It is powerful, but it carries uncertainties. Astronomers immediately recognized that some of these apparent tensions might disappear once more precise measurements became available, and that is exactly why follow up observations became so important. Over the next several years, Webb conducted spectroscopic observations. Spectroscopy provides much more reliable redshift measurements. Instead of estimating distance from colors, spectroscopy directly identifies characteristic emission and absorption features in a galaxy's light. What happened next surprised many researchers. Some candidate galaxies turned out to have lower masses than initially estimated. Others remained surprisingly massive. The tension weakened in certain cases, but it did not disappear entirely. In fact, newer studies continue to find evidence that massive galaxies, quenched galaxies, and highly evolved structures may have formed earlier and more efficiently than many models predicted. That distinction is critical. The data do not currently prove Lambda-CDM is wrong, but they do suggest that some assumptions about star formation efficiency, feedback processes, or early structure formation may require revision. And that brings us to the central question. If these galaxies are genuinely more massive than expected, how did they form so quickly? Scientists have proposed several explanations. The first is that star formation in the early universe may have been far more efficient than previously believed. Perhaps the first galaxies converted gas into stars at extraordinary rates. Perhaps the mechanisms that suppress star formation in modern galaxies had not yet become effective. If so, galaxies could grow far faster than older simulations predicted. The second possibility involves observational biases. Estimating stellar masses at extreme distances remains difficult. Dust, active galactic nuclei, and unusual stellar populations can all affect measurements. As Webb gathers more data, some of the apparent discrepancies may continue shrinking. The third possibility is the one that attracts the most attention. What if there is new physics involved? What if dark matter behaves differently than assumed? What if the earliest universe experienced conditions not fully captured in current models? What if our understanding of cosmic structure formation is incomplete? These questions remain open, and this is exactly why cosmologists are excited, because the most interesting moments in science occur when observations force theory to evolve, not when theories are confirmed, but when nature reveals something unexpected. And according to many astronomers, Webb may be doing exactly that. Now that we understand why the James Webb Space Telescope has sparked so much discussion, we need to talk about something equally important. The Webb galaxy discoveries are not occurring in isolation. They are arriving at a time when cosmology is already facing another major challenge, a challenge that has been growing quietly for years, a challenge known as the Hubble Tension. To understand why this matters, we need to step back and examine one of the most fundamental measurements in all of astronomy. How fast is the universe expanding? This quantity is called the Hubble constant. Named after Edwin Hubble, it describes the rate at which galaxies move away from one another due to the expansion of space itself. For decades, astronomers have refined measurements of this value, and for decades, the process seemed straightforward. Then something strange happened. Two of the most reliable methods began producing different answers. The first method uses observations of the early universe. Scientists study the cosmic microwave background, the faint afterglow left behind roughly 380,000 years after the Big Bang. Using data from the Planck mission and applying the Lambda-CDM model, researchers derive a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method uses nearby astronomical objects. Astronomers observe Cepheid variable stars and Type 1, a supernovae, to build what is known as the cosmic distance ladder. This approach consistently produces a value closer to 73 kilometers per second per megaparsec. At first glance, the difference may seem small. It is not. The discrepancy is now large enough that many researchers believe it cannot be explained by random statistical fluctuations alone. Multiple independent analyses continue to find significant disagreement between the two approaches. Why is this important? Because both methods should produce the same answer if our understanding of cosmic evolution is complete, yet they do not, and that means something is missing. The Webb galaxy anomalies and the Hubble tension are different problems, but they point toward a similar possibility. The universe may not be behaving exactly the way our current models assume. That does not mean the entire framework is wrong. It means there may be additional physics we have not yet identified. This is where things become genuinely fascinating. Scientists have begun exploring several possible explanations. One idea involves dark matter. Dark matter remains one of the greatest mysteries in modern physics. We know it exists because we can observe its gravitational effects. Galaxies rotate too quickly for their visible matter alone to explain. Galaxy clusters contain more gravitational pull than ordinary matter can provide. Large scale cosmic structures require additional unseen mass. Yet, despite decades of searching, scientists still have not directly detected dark matter particles. The standard cosmological model assumes dark matter is cold. That means its particles moved relatively slowly when structures first began forming. Cold, dark matter naturally produces the bottom up formation process predicted by Lambda-CDM. Small structures form first, large structures emerge later. But what if dark matter behaves differently? Some researchers are investigating warm dark matter models. Others are studying ultralight axion like particles. These particles would behave almost like waves on galactic scales. Instead of forming structures exactly as standard cold dark matter predicts, they could potentially alter the timing of galaxy formation. Such models are not new. What has changed is that Webb's observations provide a fresh set of data against which these theories can be tested. Another possibility involves primordial black holes. Most black holes form after massive stars collapse. Primordial black holes are different. These hypothetical objects could have formed directly from density fluctuations shortly after the Big Bang itself. If sufficiently massive primordial black holes existed in large numbers, they could have acted as gravitational anchors around which matter accumulated rapidly. Galaxies might have formed faster than standard models currently predict. Researchers continue investigating this possibility, though observational constraints limit how many primordial black holes could realistically exist. The idea remains intriguing because it naturally accelerates structure formation without requiring a complete rewrite of cosmology. Then there is modified gravity. This is where theoretical physics becomes especially interesting. For over a century, Einstein's general relativity has passed nearly every observational test thrown at it. From gravitational lensing to black hole imaging to gravitational waves, general relativity continues to perform remarkably well. Yet every successful theory eventually encounters limits. Newton's laws worked beautifully until scientists began studying extreme speeds and strong gravitational fields. At that point, relativity became necessary. Some physicists wonder whether something similar could happen again. Perhaps general relativity is incomplete under the extreme conditions of the early universe. Perhaps gravity behaved differently when the cosmos was only a few 100 million years old. If gravity were slightly stronger during those early epochs, structures could have formed more rapidly. Galaxies could grow larger sooner, and some of Webb's observations might become easier to explain. Several modified gravity frameworks are being investigated. Most remain speculative. None has yet emerged as the definitive solution, but the possibility remains firmly on the table. This brings us to extra dimensions. One of the more intriguing theoretical ideas developed over recent decades is that our familiar universe may represent only part of a larger, higher dimensional reality. In certain brain world models, including the famous Randall-Sundrum model, our observable universe exists on a four-dimensional surface embedded within a higher dimensional space-time. In these scenarios, gravity can extend into dimensions inaccessible to ordinary matter. Under certain conditions, gravitational behavior could differ from standard predictions, particularly at very high energies and very early cosmic times. No evidence currently proves such models explain Webb's observations. However, the fact that cosmologists are once again discussing modifications to gravity, dark matter, and early universe physics demonstrates how seriously these observations are being taken. Meanwhile, NASA and observatories around the world continue gathering data. The goal is simple, is before rewriting cosmology, scientists want overwhelming evidence. That evidence is arriving through multiple channels. The National Aeronautics and Space Administration, the European Space Agency, and numerous international research teams are conducting follow-up campaigns using Webb alongside facilities such as the Atacama Large Millimeter Array, the Keck Observatory, and the Very Large Telescope. Researchers are measuring gas content, star formation rates, chemical abundances, galaxy dynamics, black hole populations. Every new observation helps narrow the range of possibilities. Perhaps the galaxies are not quite as massive as originally estimated. Perhaps early star formation was dramatically more efficient. Perhaps dark matter behaves differently than expected. Perhaps something even more surprising awaits discovery. The most important point is this: science is working exactly as it should. Contrary to sensational headlines, astronomers are not panicking. They are investigating, they are testing, they are questioning assumptions, and they are doing what scientists have always done when confronted with unexpected evidence. They are following the data. History suggests that periods like this often precede major breakthroughs. The unexplained orbit of Mercury eventually led to general relativity. The ultraviolet catastrophe helped launch quantum mechanics. The unexpected acceleration of cosmic expansion led to the discovery of dark energy. Each time, observations exposed limitations in existing theories. Each time, physics emerged stronger afterward. That is why many cosmologists view the current moment as so exciting. The James Webb Space Telescope has opened a new observational window unlike anything humanity has ever possessed. For the first time, we are studying the earliest generations of galaxies directly rather than inferring their existence indirectly. And the universe appears determined to surprise us. Maybe the standard cosmological model will survive with only modest revisions. Maybe improved simulations will explain the galaxy's Webb is finding. Or maybe we are witnessing the first hints of a deeper theory that will eventually extend beyond Lambda-CDM. Nobody knows yet. That uncertainty is not a weakness, it is the frontier. Right now, observations are arriving faster than explanations. The data are leading, theory is trying to catch up. And throughout the history of science, those have often been the moments when the most important discoveries were waiting just around the corner. So here is the question: if Webb's early galaxies, the Hubble tension, and future observations continue pointing toward cracks in our current understanding of the universe, what do you think comes next? A refinement of existing cosmology, a new form of dark matter, a modification of gravity, or an entirely new chapter of physics that nobody has imagined yet? That answer may define the next generation of cosmology.